So in the previous video, we've seen how to find the inverse of a matrix. And in this video, we're going to see the application, one direct application of finding the inverse, and that's solving a system of equations. Now, we've already seen that we can use the substitution method, the elimination method, and we can take a matrix and put it in row-reduced form to be able to solve a system of equations. Yet another way is to take our system of equations and write it as a matrix equation and solve for the unknown vector, this vector x. And we can do that by multiplying both sides by the inverse. So what we have is this matrix equation. We're writing this as ax equal b, where a consists of a matrix of the coefficients in the system of equations. B is the right-hand side, and this capital X, that represents the vector of variables that we have. So when we solve for that capital X, we have solved our system. We can write the system of equations, right? We have this system of equations that is, as an example, 2x plus 3y equal 5 and 3x plus 5y equal 8. We can write this in the form ax equal b by first writing the matrix A consisting of the coefficients 2, 3, 3, and 5. This capital X is a vector. It's just a 2-by-1 matrix consisting of the variables x and y. And then B, that's the right-hand side. That's the 2-by-1 matrix, or a vector consisting of the right-hand side, 5 and 8. And so we can proceed with solving for this x and y by multiplying both sides by the inverse of A, right? Because when we multiply the matrix A times A inverse, that leaves us with the identity. Right? You can think of the identity as the number 1, right? 1 times anything is itself. So in this case, if we're multiplying by the inverse, right, and we have the identity times this vector xy, that just leaves us with xy, and whatever that xy is equal to on the right hand side will be our solution. Okay, so the first thing that we need to be able to do is to find the inverse of A. And then we'll multiply both sides by that inverse, simplify, and we've got our answer. So what is the inverse of A? Remember our formula for the inverse of A, 1 over AD minus BC times D negative B negative C A, to where A is equal to 2, B is equal to 3, C is equal to 3, and D is equal to 5. So A inverse is 1 over 2 times 5 minus 3 times 3, 5, negative 3, negative 3, 2. Now the determinant, right, this AD minus BC, 2 times 5 minus 3 times 3, that's 10 minus 9, which is 1. So the determinant is 1. So 1 divided by 1 is just 1. So the inverse, right, we're multiplying 1 by every entry, which does not change anything. So our inverse is 5, negative 3, negative 3, 2. And now our next step is to multiply both sides of this matrix equation by the inverse. I'm going to show multiplying the left-hand side by the inverse, but it's not really necessary because I know that this is going to cancel out with this coefficient matrix by definition of the inverse. It does matter which side you are multiplying on, because we do not have the commutative property of multiplication with matrices. If you multiply the left-hand side of the equation on the left, you also need to multiply the right side of the equation on the left side as well, right? Right. So if you're putting this inverse on the left side, you need to put this inverse on the left side as well, on the other side of the equal sign. Okay, now I already know, since these are inverses, if I were to multiply this, it would just give me the identity matrix. There is no need of going through that calculation. Save yourself some work there. But we will want to perform the multiplication on the right-hand side. All right, so we'll do some quick multiplication here. It will end up as a 2 by 1. 5 times 5 plus -3 times 8. 5 times 5 is 25. -3 times 8 is 24. So 25 minus 24 is 1. And then I'll multiply the second row by the column. -3 times 5 plus 2 times 8. -3 times 5 is -15. Plus 2 times 8 is 16. -15 plus 16 is also 1. So xy is equal to 1, 1, right? So this is equivalent to saying that the ordered pair solution is 1, 1. X equals 1, y equals 1. The ordered pair, 1, 1, is where the graphs of these two equations would intersect. Okay, now that's an alternate way of solving that system. Right, so what's the benefit of this? The benefit is if we were to change the right-hand side, but the coefficient matrix remains the same, we don't have to reinvent the wheel. We can still use the same A inverse. And so all we would do in order to solve the system is to perform this multiplication again. Since these would be the same numbers, the only thing that's changing is here. And you'll find that very often in business, if your numbers change slightly in the problem, but the overall parameters remain the same, it makes it much easier to find the solution of multiple problems. All right, we'll look at one example here, an application problem. We have a rental company that is purchasing compact and full-size cars to expand its fleet. The average cost is $10,000 for compact cars and $24,000 for full-size cars. If a total of 800 cars is to be purchased with a budget of $12 million, how many cars of each size should be acquired? All right, so we've got two variables. Right, how many compact cars should be purchased? How many full-size cars should be purchased, right? So we've got this X and the Y. Right, X is the number of compact cars. Y is the number of full-size cars. Now, if we have two unknowns, we need two equations to be able to solve for them. So we need two different equations, right? We can talk about the number of cars, right? We know that we should have a total of 800 cars. So the number of compact cars plus the number of full-size cars should equal 800. And we know how much we have to spend and how much each one costs. The average cost of the compact car is $10,000. So if I multiply $10,000 times the number of compact cars plus 24,000 times the number of full-size cars, that should equal 12 million. Okay, so for the purpose of the lesson at 5.6, I'm going to set this up as a matrix equation and solve for X and Y using the inverse. But I have my two equations. I can write this in as a matrix equation by writing the coefficients, 1, 1, 10,000, 24,000. And then my variable vector, and then the right-hand side, 812 million. So my next step is to find the inverse of my coefficient matrix. Okay, so the inverse is 1 over AD minus BC. Then I switch A and D, and I make B and C negative. So I'm going to determine it. 1 times 24,000 minus 1 times 10,000, that is 14,000. So 1 over 14,000, and then 24,000, negative 1, negative 10,000. So multiplying through by this 1 over 14,000, 24,000 divided by 14,000, I can reduce that as 12/7. 1 over 14,000 times negative 1, which is negative 1 over 14,000. Negative 10,000 times 14,000 is negative 5/7. And then we'd have a 1 over 14,000 here. So that's my inverse. All right, so I'm going to multiply both sides by the inverse. I know the left-hand side of the equation, when I multiply by the inverse, that's going to essentially cancel out that coefficient matrix. So I'm going to skip showing that step and just come right here and say that my variable xy vector is equal to this inverse times the right-hand side, 812 million. All right, so we're going to perform the matrix multiplication. We're multiplying the first row times the column, 12/7 times 800 plus negative 1 over 14,000 times 12 million. I'll let you help me with that calculation. Round that to the first decimal place. You will hopefully agree with me that we have 514.3. And then for the second entry, we're multiplying the second row times the column. Negative 5/7 times 800 plus 1 over 14,000 times 12 million. And we should be getting an answer of 285.7. Now we're talking about cars here, so we can't have decimal values. So let's round to the nearest whole number, 514 for X and 286 for Y. So we should have 514 compact cars and 286 full-size cars to satisfy our requirements in this specific case. Now, if our parameters changed, if the average cost remains the same, but let's say if we wanted a different number of cars, we had a different budget, we could easily and quickly rework this problem since the coefficient matrix remains the same. Right, all I have to do is change these two numbers and perform the multiplication again. So that way I don't have to start the problem over, which is the advantage of using these matrix equations. If you were to use substitution or elimination, or even using row reduced form with the matrix, you would have to start all over again. But here we can store any useful information, any information that does not change, to help us find the solution of different scenarios very quickly.